Okay, so we're just going to kind of pick up where we were yesterday. We're going to optimize another problem. This one's going to actually be involving a cylinder. So it is a little bit more involved because things that involve a cylinder, like formulas, are a little bit more complex than just rectangles and boxes like yesterday. But you're ready. At least I want you to be ready. So here's the cylinder problem, or as it says up here, a can. A can. I know you might have to write down some things. I just realized that sometimes that's what happens when you have to take notes. So if you want to write down this little sentence, you can. If you want to paraphrase it, obviously the math is where I'm going to jump in with you. Okay, now it seems pretty straightforward. I mean, we basically have one piece of information, but actually what I hope to show you is that we actually have a little more than that. Okay, we have more than just this volume thing that kind of stands out. And that's where we kind of have to start the problem. We have to start the problem by thinking about a primary and secondary equation. Okay, now you're going to want to use this strategy. Even though we only used it kind of directly one time yesterday, it's really a strategy that works every time. And your primary equation is always what you're trying to optimize. Now I have it highlighted in red to try to make it stand out, but I want students to understand that it's always like a word. The primary equation is a word. It's, in this case, the surface area. Because really the surface area of a can is kind of like all the metal. It's all the outside parts. It's what the can is made out of. So it's what we're trying to use the least amount of. I know it says material, but that refers to the surface area. Now, are you picturing the surface area of a can? There's kind of like the sort of the side of the can, but then there's also the top and bottom of a can. So the surface area actually comes from two parts. Okay, now this is basically a geometry idea. If you're like, I don't remember, I'm just trying to make you think a little bit about how we can recreate what's true about the area of a can. Okay, the part around the outside, if you unroll it, it would definitely turn into a rectangle. Basically, the part around the outside has a length and a width. Okay, now the length is going to be like what you kind of see here, how wide is the can. But the length is like, if you unroll it, it's like unrolling the circumference. So my length times width actually involves a circumference of a circle, which is 2 pi r, and a height of my can, which we'll just call it h. Now 2 pi rh, I know it looks like a geometry idea because it is, but that's the area of the outside of the can. Then we have the tops and bottoms. Now that's actually a little bit easier because those are just circles. It's nice to know that the area of a circle is pi r squared. But there's 2 circles, so there's 2 pi r squareds. Okay, now look, if I had just written that down 2 minutes ago, we would kind of miss out a little bit on what I want you to be able to do, which is to think. But if you're like, I don't remember that formula, you could look it up, you could ask, or you could do a little bit of thinking. Okay, all of those is part of this lesson. Okay, but how about the secondary equation? The secondary equation, Sometimes we don't know why we need it until we finally get into the derivative. But basically, the secondary equation is the other information. It's clearly the volume. So it's pretty easy to say volume equals 1,000. But as you're going to also realize, you want to think of it like a formula. Okay, now the formula for the volume of a can, when I learned this in geometry, I always thought of it like the bottom of the can being stacked up sort of an infinite amount of times. If you take the bottom of the can, its area, which is pi r squared, if I take that area and I stack it up to make it like three-dimensional, then I would just be multiplying it by the height. So we get maybe a formula that maybe looks familiar. If you really dig back to geometry, it's pi r squared h. Okay, now we've kind of opened up a bigger can of worms here, right? No pun intended. It's a little harder problem because the formulas are a little more complex. What you want to realize is that it's the surface area formula that we're going to derive. Derive means do the derivative. Now, look at this. Do the derivative of this? Yep. Except I don't want to do it with two variables. So there's always a substitution that takes place. Now, this problem has choice. I can either substitute for r, which we're going to find out we don't want to do, or I could substitute for h, which we'll find out we do want to do. Why do I want to substitute for h? Simply because it's simpler. If I substitute for h, it only gets substituted in one place. If I substitute for r, I've got two places, plus I got this square. So that type of thinking causes you to go to the secondary equation and solve it for h. Again, we're going to solve it for h because we've thinked a little bit into the future, and the future says that it's going to be easier to do that substitution. Now look, it's not hard to solve this for h. Just divide both sides by pi r squared. So I end up with 1,000 divided by pi r squared to be the same as h. So we're kind of still in the pre-steps. The pre-steps is trying to get everything ready. So we're going to do a little substituting. My surface area, I'm just going to abbreviate that now as SA, but my surface area takes on a slightly different look. I end up with 2 pi r, but then I substituted 1,000 over pi r squared for h. And then over here, I still have 2 pi r squared. We're still in the pre-steps. Maybe you're kind of wondering where this is all headed. The answer to that is it's headed towards a derivative. The reason I'm still in some pre-steps is because it's usually easier to do algebra before calculus. So, like, why wouldn't you cancel those pi's? And why wouldn't you reduce the r's? And why wouldn't you take 2 times 1,000? Well, you would. So we get 2,000 over r plus 2 pi r squared. It's interesting to note, that is, if you're interested in this, that this equation is really an equation for the surface area of a can that's going to have a volume of 1,000. Okay, it's kind of like we blended the two equations together. So now I have an equation for the surface area that matches my volume. And of course, if I want to find the maximum, or in this case, actually the minimum, because I want the least amount of area, so I want to find the minimum, then we're ready to do the derivative, just like we've done the derivative of any function. Yes, the function's a little complicated. It's got a fraction. Yes, it's got a pi in it, but truthfully, that pi is just a coefficient. So we're going to do the derivative. We're going to optimize. What I'm trying to sort of sell to you here is that it's the same thing that we actually were doing before break. It's obviously just a formula this time. Surface area prime. Yeah, you can say that. I mean, you should. You should put a prime symbol there because you're actually changing the equation. I actually do want to pause on purpose and give you guys an opportunity to think about the derivative of this. I hope that you'll think about it. Maybe you'll realize that there's something you have a question on. Maybe you'll say, oh, good, I got it right. Love to see you get the fraction right. As a little hint, we did that yesterday. Remember how to think about a fraction? This is meant to try to trigger something in you. And I keep saying it, there'll be a time where I don't write that. That time will be when everybody's getting that right. So we want to think about a negative exponent so that you can bring down a negative exponent. If you subtract from a negative exponent, it gets more negative, but eventually that's going to flip back over to be positive. So you might as well do that. That's the derivative of that fraction. This is just a good old bring down the exponent, subtract from it. I think we're going to get a 4 pi r. 4 pi r. R's to the first power. Okay, now remember, and sometimes we kind of forget because we're now getting into some harder problems, but this is just a derivative. And it's supposed to have a maximum or minimum when it's equal to 0. That's a pretty key idea because remember, the slope is equal to 0 when you're at a high point or a low point. So we're kind of like saying, okay, when does that happen? Okay, now you should kind of look at this through sort of an algebra lens. And, there's a couple different things you could do here. Some people would say, hey, can I multiply by a denominator? Yeah, you can multiply by a denominator. That will kind of get rid of the denominator. Some people will say, can I make a common denominator? If you make a common denominator, it's interesting, you're still, in a sense, multiplying by the denominator. So it actually works either way. I'm going to actually go the common denominator route because I know that it's going to be helpful for some other problems. You see what I did here? I put an r squared in the bottom, but that means I need to put an r squared in the top. It's going to get me r cubed. It's going to get me r cubed. I also rearranged it because it just looks a little better to put minus 2,000 after 4 pi r cubed. Now, in theory, a derivative will have a critical point when it's either equal to 0 or when it's undefined. To say that the bottom is equal to 0 is to technically take advantage of that undefined option. It's kind of a little bit of a detail, but it is true. And the only thing I'm going to say about that is the only way that r squared can equal 0 is if r equals 0. And I just want you to think for a minute, how big is my can? How big is my can if it has a radius of 0? Not real big, right? So that technically is a minimum. But in the case of this problem, it's kind of a minimum that we can kind of disregard. Because again, if I don't have a can, I don't have any material. Again, we kind of disregard it for the sake of the application. But technically, it's true, which is what I'm trying to say to you. But it's this guy up here that's going to produce like a sort of a viable answer. 4 pi r cubed minus 2 grand equals 1,000. You can kind of work that out. I hope you add 2,000, divide by 4 pi. It's a calculator thing. I would expect that you would be using a calculator. You're going to get a decimal. You actually would have to take the cube root of both sides. If you don't like taking the cube root of both sides, remember that you can raise both sides to an exponent of 1/3. If you raise both sides to an exponent of 1/3, that's equivalent to cube rooting. Now, you don't get a plus or minus when it comes to cube roots. That's because it's odd. So you basically take 2,000 divided by 4 pi, slap a cube root on it, and we have a radius. It's 542. Make sure you're comfortable getting that. Okay, now 542 is a critical point. Sometimes students will say, well, it's got to be the right answer, right? Well, my answer to that is, let's check to be sure. Now, this does take a little extra time, and it requires you to be careful about all these fancy numbers. But if I plug some number in on the left side of 5.42, I don't know, 3. And if I plug a number in on this side, I don't know, 8. Doesn't actually really matter. But if I plug them in to the derivative, okay, now I'm pointing up here. I guess I could also point right here. But basically, if I plug into my derivative, I can check and just make sure that this side is negative and this side is positive, which means that my graph does go down and then go back up, which means that 542 really is a minimum, okay, which is good, okay? That's kind of what we hoped it was going to be. You say, what if it wasn't? Well, then there was a mistake somewhere, okay? It has to come out to be a minimum to be correct. Yesterday, near the end of the period, I kind of quickly finished that problem. I know I did that, but let's make sure that we finish the problem. The answer to the problem is not 542. The answer to the problem is the least amount of material. In other words, the smallest surface area. Okay, now my surface area formula up here would allow me to plug in 542. It would also require me to plug in h. Okay, so I have some decisions to make. Do I want to find h? I could find h. It's kind of like a value that would match with my 542. I'm just going to show you what it is, but I would assume that you understand I'm plugging in to this formula. So that comes out to be 10 and some change, 1084. If you're really kind of clicking right now, you would say, Ms. Naylor, this is a surface area formula. Yeah, it's the surface area formula that already took account for h. What I'm saying is you can actually plug 542 in here and sort of be one and done. Okay, but you got to finish the problem. You have to actually find the surface area. Okay, and because it's a word problem, kind of like you to label it so I know that you know that this is actually the minimum surface area. So give her a little label. Okay, whether you plugged it in here, whether you found h and plugged it in here, but we end up with 553. I would assume that you can get that on a calculator if you need to. It's 553, and a little bit of science comes into play here. Since this thing's in milliliters, maybe you remember from your science class that means that the dimensions would be in centimeters. Thank goodness for the metric system. We can kind of interchange a little bit with volume and, square centimeters because it's area, but the dimensions would be, again, milliliters into centimeters squared. Now you can kind of see why I'm only going to ask you to do 2 of these problems with a partner, well, a pseudo partner. Okay, I'm going to ask you to do 2 of them and really get them right. Let's do another one. Okay, I still got you here, and this one kind of has a little different flavor to it. Here, I have it up on the screen. This one, we're trying to find something known as a rectangle that's inscribed. The concept here is inscribed. It may depend on your math class last year. It may also just depend on your teacher and your memory. But you may have seen a problem like this. You just would have approached it, you would have finished it with a different approach, meaning you would have finished it with algebra instead of calculus. But sometimes students will say that they kind of remember something like this. And yeah, I'm graphing y equals root 4 minus x squared. Okay, I don't expect that you just can graph that without a calculator. So part of this problem requires us to understand that inside that semicircle, now it might not look perfectly like a semicircle, but it is. Inside that semicircle, we can put a rectangle. To put a rectangle in there, to inscribe a rectangle in there is to understand that the vertices of the rectangle are dictated by the curve. You see, it's kind of like the curve is restricting how big that rectangle can be. That's what it means to be inscribed. The vertices are actually on the curve. Now, there's other vertices which also end up down here, etc. But as you can tell, they still are based on the curve. How big can this rectangle get? That's really the question. How big can that rectangle get? And although you probably don't need to draw a second one, I just want to make sure we understand that we don't know. We don't know. Maybe this rectangle is bigger. It's still inscribed because the vertices are determined by the curve. Or maybe you're saying, well, Miss Naylor, wouldn't it be kind of like one in the middle? Okay, maybe it is. Okay, maybe it's this one, kind of a little bit more in the middle, or it almost looks like the one I already drew. But the point is that we need to figure out how big this rectangle is going to be. Okay, now this problem students tend to like a little better because it doesn't get all fancy with geometry formulas. It's actually a little bit more of just thinking algebraically. And it's understanding that since we don't know how big this rectangle is going to be, that's where we have to start. We have to start by understanding that that dimension can only be labeled as it always is, as x. Now you say, wait, I'm supposed to just know that? Well, you have to realize that that's the only thing that we know about this problem, that there's an unknown dimension, and x is that measurement from the middle to a vertice. Now, likewise, we could argue that this is x. We don't want to think of it as negative x because we're talking more about like dimensions here, so sort of like absolute dimensions. Okay, but we're getting somewhere. Where are we getting? We're getting to a length. We're getting to a length. I hope that you would say that the length here is 2x. How about that dimension? Do you realize that it's also unknown? It's unknown, but we can describe it. Not as x, but as y. Okay, of course, y is always a vertical dimension. Now you'll realize that we don't want to have two variables. We don't want x and y. But the good news is we know what y equals. Y equals something with x. It actually equals the square root of 4 minus x squared. Now, what I just did here, I'll sort of confess, is I kind of jumped into the problem, which was fine. It's probably what you're going to do also, and started to just kind of describe things that are true. Technically, this is the secondary equation. Technically, it's relating different parts of the given. It's the primary equation. This is the part where I sort of confess that I maybe should have done this first, but it doesn't matter as long as I go do it. It's the primary equation that's maybe the most important. And so, do you realize what it is? Sometimes it's kind of too easy and we make it hard. It's that red word up there, area. It's area. The primary equation is area. Don't miss it because of the complexity of our sketch. In fact, don't make it too hard. The area of a what? Of a rectangle. So yeah, it's length times width. And again, sometimes students make this one too hard because they're looking for a complex equation. But it's just length times width, and we kind of already did the work to figure those two things out. And this is where that little substitution comes in. Okay, whether you do the problem with a sketch, whether you do the problem a little bit more with algebra, it all kind of goes to the same place. And that is, it goes to an equation that's going to have one variable, x, for this problem. And that one equation with one variable is something that we can optimize. Okay, that's supposed to be code for derive, derivative. Okay, and that'll probably be a good place to kind of pick up when you guys come back. Just so you know, I'm going to ask you, hey, why don't you see if you can do the derivative? How are you going to do the derivative of 2x and a square root of 4 minus x squared? Okay, you can think about it a little bit, or just be ready when you come back. We've actually done a problem like this. It would have been quite a while ago, but it's always possible that you recognize some of the algebra. So we're using the product rule. First derivative of second. I want you to take a careful look at this. It really is sort of a calculus marvel. Okay, 2x is just the first, but the derivative of the second, I changed it to 1/2. Of course, I brought that down. I left the inside alone. I continued to finish the derivative of the outside, changing it or subtracting it to be negative 1/2. But then I'm sort of wondering, how'd you guys do here? A for the day, if you put the chain rule at the end of that derivative. Okay, if you didn't, fix it up so you can get that A for the day. Now that's just the first derivative of second plus the second derivative of the first, which is actually quite a bit easier because the derivative of the first is just 2. Careful if you're kind of looking at this and saying, are we going to have to do a problem like this? Yep. Somebody, more than somebody, is going to pick a problem out of that group of papers that you'll see some square roots. Okay, now, and we're not done because, well, you got to set this equal to 0. And unless you're like the algebra master, you can't solve that equal to 0 like that. So you can write equal to 0, but we're really not ready for that. Okay, what we have to see here is that this thing is going to require some common denominators. That's looking quite a bit into the future, but this exponent is going to become a denominator. And so eventually common denominators kind of pull this together. How about stuff like this, right? I mean, if you can do some algebra, do it. But, you know, I think that that's pretty much all we can do as far as canceling. X times x, x times negative 2x is negative 2x squared. And then here comes this denominator. which that doesn't look too bad. We can work with that. Now, a student that realizes that common denominators are coming down the road would put the square root into the same form as the rest of this problem. So we're going to make the square root turn into an exponent form. Okay, and again, you actually have done a problem similar to this, where we have a common denominator that involves an exponent of 1/2, so that I can also multiply the top by that exact same common denominator. Maybe you get to the point where you realize that what's really going to happen here is that these exponents are going to conveniently add to be 1. So what I'm saying is maybe you skip some steps. I could see that you could do that. So we're going to add these exponents, again, to be 1. Everybody likes an exponent of 1. You don't have to mess around with any FOIL method or anything. Okay, so we're trying to get this crazy thing to be in a form that we can solve equal to 0. I think we're there. If you combine some like terms up top, you end up with a minus 4x squared. You also get an 8 because you do some distributing. But again, we get a nice little 8 and a minus 4x squared. You might notice that I've purposely done some problems with fractions. I just want to give you guys more exposure to this, that you can do these. I've not really tested you on a problem like this yet, but I have graded you on some. So remember, we're setting this equal to 0, but we're also setting it equal to undefined. That's important because when x equals, or when the derivative equals 0, we get critical points, but when the derivative is undefined, we also have the potential for a critical point. Okay, so we don't want to rule out both these options. Can we just kind of do a little mental algebra? I mean, you can solve it. I think we're going to end up here with x squared equaling 2. And if x squared is equal to 2, that means x equals plus or minus root 2. Down here, the only thing that's going to make this equal 0 is if 4 minus x squared is equal to 0. So again, we get a little bit of mental algebra. We're going to get x squared equaling 4, but that means that x equals plus or minus 2. Interesting. I hope that we realize that both of those 2's, I'm talking about root 2 and 2, both of those parts, numerator, denominator, seem to be some valid numbers, like numbers that we should be thinking about, numbers that we should be putting on a number line. So root 2 and 2 can go on a number line. Now you'll notice I left out the negatives, okay, because even though there's a lot going on here, the negative x, if we go back to this sketch, the negative x, it's like the same thing. So I don't need to sort of have too much fat over there. The negative x is just going the other direction. Okay, so I can just focus on the positives. Okay. Hey, this is your derivative. You know, I was kind of going back to this derivative, but I don't want to plug into that thing. I'd probably plug into this thing. And you could plug in some numbers that are in each of these spaces, 0. This gets a little fancy here because there's not too many numbers between root 2 and 2. 1.5 if you really have to do that. But again, I can technically plug in into each of those spots. I was just looking at my notes and I noticed something that I might as well share with you. There's actually a good reason that we wouldn't need to plug in 3. And I'm not saying that 3 is not greater than 2, but there's actually a good reason that my number line can stop at 2. Okay, and the reason has to do, again, back with this sketch. If you think about it, the y value can never exceed, the x value can never exceed 2, else we're going to end up with a y value that doesn't make sense. Again, if I plug in an x value bigger than 2, I get a negative under the square root. So there's not going to be anything over there. There's not going to be any graph over there. We actually could technically stop the graph at 0 because same thing, we're not going to end up with a negative. But still, we can come up with we can get what we need. We can discover that it's positive on the left, that it's negative on the right. That means the graph goes up. That means the graph goes down. And that makes it pretty certain that this one's the max and this one's the min. Interesting, the number 2 would be a minimum, but according to this problem, we're trying to find a maximum. So we actually, don't need anything else but root 2. When you answer your question, and maybe I should say, make sure you answer the question. But when you do that, you want to think about everything we've done. There's no reason I can't say x equals root 2, but it'd be better to say that when x equals root 2, well, I can give the area, which I do need to give. I can also give like the dimensions. The dimensions would come from thinking about what happens when I plug in root 2. I could plug in root 2 to any of these things here. It's not really part of this problem, but I know there's a problem that you guys will do where I ask you to give the dimensions. So we could say something like, if x equals root 2, then that means that we have 2 root 2s for the width. The length is just going to be what happens if I plug root 2 in here. Okay, that actually comes out to be root 2. There's a lot of root 2s in this problem. Make sure you understand that the length is root 2 because that's what you get when you plug in an x value of root 2 right there. So we do a little math, we get the length. And then your area is what happens when you multiply these. Or you could plug back into the area equation. Your area equation is right here. But it's kind of neat to multiply these because, well, it just works out to be 4. And I probably should have said maximum area, so shame on me, but we get a max area of 4. Optimization. Fun. Okay. To keep the fun going, optimization fits nicely into one other type of problem, not like a geometry problem. I mean, most of the problems we've done had something to do with geometry. We say it's more of a business calculus application. Now, business calculus, for those of you that if you go to college and you are going to be a business major, this is what you'll focus on. I actually had a student come in over December and he needed a little help with his business calculus. I found out that I too need a little help with business calc because it's like a whole different branch of calculus. But what I'm doing is kind of giving you guys a little exposure to it. Okay, now I'm not trying to spin this like I don't know what I'm talking about. I'm just being honest with you that I only have so much knowledge. And what I'm showing you here is enough to get you guys to realize that you can do some interesting economic or business optimizations. Simple business ideas usually revolve around these 3 equations: revenue, cost, and profit. Again, simple. The revenue is what you get from selling so many glasses of lemonade. Okay, the revenue is what you get from selling the lemonade. The cost, well, you understand the cost is what it takes to make the lemonade. Of course, the revenue, that's what you're really concerned about. That's the difference between, the profit, the profit is what you really are interested in, which is the difference. Okay, I hope you're looking at these three words and saying, okay, yeah, that's basic economics. And by the way, if you take a business calculus class, I saw it because the student came in and showed me, you will talk about these things. And you'll talk about what I'm going to show you next. You're just going to go a lot deeper. Maybe you can come back and tell me a thing or two. So when you do the derivative of these three equations, when you do the derivative, you get what's known as a marginal. Now, on one level, a marginal can be an easy idea for us today. It's a derivative. Like, I definitely want you to say, okay, a marginal is a derivative. On the other level, a marginal, it really does represent something. But I'll confess to you that it's hard for me to fully explain it because I always think of a derivative as a slope, and it still is. A derivative is a slope. But what does that mean when you're talking about money? And usually the way that it's described to students on sort of a beginner's level is that it's like the cost or the value or the price of one more. So if I sell 10 cups of lemonade, how much did that cost? But the next cup that I sell, like one more cup. Now you say, well, why wouldn't that just be, one more cup? Well, because when you're thinking or comparing it to all the cups, okay, it may not end up being the same amount of profit. You might make more profit. You might make more profit selling the 11th cup versus just selling that first cup. Okay, so sometimes profit can change. Usually you make more profit when you start selling more, okay, because you've already taken care of a lot of your cost. Again, some of you that take a business calculus class, you'll dig into that more. So here's sort of the thing that everybody can do. I'm serious, like, this will be easy. You can do it. And it involves a maximum profit. Usually that's what companies want to do. They want to get a max profit. And the cool thing is that happens when basically the marginal of the revenue is equal to the marginal of the cost. So basically when the two derivatives are equal. Now I can show you some stuff like on a graph, but I'm just being honest with you, I'm not going to. I realize for most students, it's kind of like, yeah, I don't really need to see that, but there's reasons for this. And maybe if you take calculus in college for business, you'll see some of those things. But basically the reason behind this is a slope idea. It's like two slopes that are equal. And there's a little more that I could show you on a graph. It is in the book if you'd want to see. Again, it's all right if you're like, that's all right. Let me show you one more thing that fits with business. I know it seems like I'm kind of giving you some formulas. It turns out that these are kind of the easy problems because all you're going to end up doing is just following these formulas. So here's one more idea. Now, average cost. I know it's a formula on the screen, but it's really saying something that you guys already understand. You're taking the total cost and you're dividing it by how many cups of lemonade you sold. Okay? That's what an average always is. So I take my total cost of lemonade and simply divide it by how many cups. But that works into something called a minimal cost, which again, usually we want to minimize cost. And here's the thing, a minimal cost is when an average is equal to a marginal. A minimal cost is when an average is equal to a marginal. Let's do a little example. The revenue equation is 9x. That means that each cup of lemonade you decide is either 9 cents or $9. Just go with it. But basically, that's what that equation means. You're selling every X for 9. The cost equation, I mean, you're a really smart lemonade stand owner. The cost equation is a polynomial. For some reason, the cost goes up and down. Okay, you somehow figured that out. So we've got revenue, we've got costs. Again, you're a really smart lemonade stand owner. We want to find the maximum profit. It's easy. Do you remember what you wrote down? It's just when the marginal revenue equals the marginal cost. It's basically when the derivatives are equal. Now, what we're really finding here is how many cups of lemonade, that means level, production level, how many cups of lemonade are going to give us the maximum profit. You know, kind of your target sales. Now, you might say, well, wouldn't I just want to sell as much as I can? Yeah, I guess on a simple sense, but maybe for some reason, if you start selling too much, your costs go up too far. So we're trying to look for that balance point where our revenue and our marginal revenue is equal to our marginal costs. Okay, we're basically staring at an algebra equation. Do you realize that this is an algebra equation? It just screams, set equal to 0. Set this equation equal to 0. It's a trinomial. Subtract 9 from both sides. Okay, so we get a nice little 3x squared minus 12x plus 6. Now, you could do some algebra to this. One of those things you could do is maybe factor out a 3. You could try to just factor in general. It turns out that none of those things really help because basically it's not factorable. But the quadratic formula, well, always to the rescue. So I wanted to do a problem where we use the quadratic formula. Opposite of b plus or minus square root. Well, we did it the other day. I'm going to kind of cut down to the simplified version of the quadratic formula, just so you realize that I've already done a little simplifying under the square root. And it's okay to get decimals. So we end up with 0.5 and or 3.41. Now, it might be nice if I just say, hey, we're done, but there's a little more going on here. Maybe both of these give a maximum profit. You know, maybe it's just the big one, maybe it's just a small one. It's not really something that we have to just guess. We could go to a number line, or we could plug into the profit equation. The profit equation would be the equation, as we showed up on the screen, that just comes from the revenue minus the cost. So there's a little extra thinking here, but it's basic economics. I basically can plug in my X value and figure out what profit I get. So if you sell a half of X, I don't know, a half a cup of lemonade, if that makes sense, what profit would you get? Well, you can plug that into the profit formula. It's really just going to be the revenue found from a half minus the costs found from a half. Now, keep in mind that you have to plug those into the revenue and cost equations. But once you do that and subtract those numbers, then you get a profit of $4.20. What if you sell 3.4 X's? Same thing, you can plug that into the profit equation, which really means you're going to be doing the revenue minus the cost, and now you get $9.66. So just a little different way for us to find the maximum profit by actually plugging into the profit equation, comparing the numbers. And it's pretty clear that if you sell 3.4, then you're going to get a maximum profit of $9.66. For these application problems, I want you to make a statement so that I know that you know what it is that you found. Okay, now it's going to be time for you to do the partner problems.